Hello everyone. Today we're going to look at how to loop through a string, and also we're going to consider some conditional branching in Nasm. And so we're going to learn these using a project which I've already written. And the project essentially, let's take a look on the right hand side, is the inverting of characters in a string. Say if we have say for example, if we have the word hamoyo passed, it's going to convert the word hamoyo, where capital H becomes small letter and then the rest of the letters become capital, and vice versa. Okay, so this is essentially the program in C, and over here we see the same setup. We write some prompt to the screen, we read from the standard in, then we append a null terminator, then we check if it's a value between A and small z, and when it is, we convert it back into its capital letter, and when it's capital, we convert it back into its small letter, and then we print it out to the screen. Okay, and so essentially what we're going to do here is, let me try to run this program and show you guys what I mean by that. So let's compile this, and then if we pass in case in, we pass in say hamoyo, that means the first letter H is going to become a smaller letter, and then A is going to become capital, and it's just going to be inverted. Okay, so it looks like this. Okay, so let's look back at this C code again. Okay, and so essentially when we pass in it into the standard in, we're going to have to do a little bit of computation or some little tricks in there. What I mean by that is, this. So we pass in the word hamoyo, and then our read is going to include a new line, and then of course our count is going to hold on to 7. And when we are indexing, we realize that it's from 0 to 6. So essentially the 7th value we're going to place in a null terminator. That's what we're going to do today. And so let's continue on with our code in the Nasm. It follows the same setup. This time around, the only differences that I haven't shown you guys yet is I'm going to define a few constants. It's essentially the same thing, where the syswrite is 1, the standard out is 1, and then we have our sysread and our standard in. Sysread is 0, and our standard in is also 0. That means we're doing a sysread, we're invoking a sysread call. Okay, so it's the same setup over here. Yes, because this is already defined, we write it into the data section, enter the word, and also we pass in the length of the word. Then we invoke our write system call, which is essentially this part. And because this is uninitialized, we write it into the BSS section, and we also have to invoke the read system call, of which you've already looked at, and it's this. And then what I'm doing here is now I'm defining a new variable in the .bss section, which is reserving a quad word, which is 1. And that is essentially telling us that we are reserving a 64-bit integer. And so we're going to call it the length of the input, just as the right-hand side is. And then as we've already seen, after invoking a sysread call, is going to place the value into array_x, and this value is going to be now placed into the length of the input. Okay, now why do we need the square brackets around the length of the input? And so length of is telling us that we are writing to the value at this particular memory address, okay, because we've reserved length of input at this point, and then we are writing to the memory at that address. Okay, if we hadn't added the square brackets to it, it would have just mean we are writing it to an address, and that doesn't make sense. We add square brackets to it, telling us we are writing to that memory address. Okay, and so we continue on with our program, and so we're going to have, okay, so basically we are at this point and we need to add a null terminator. So with a null terminator, we see that, yes, let me write this way, add a null terminator. So we're going to move it into the byte, which is the BF, plus the length of input, okay? And so essentially we have this line, but the problem is, if we write it this way, it means we are writing an address, we are taking the address of buff plus the address of, we are adding the address of the length of the input, and that doesn't make sense. So we ought to rewrite the length of the input into an address and then into a memory register, and then we pass it in. What I'm trying to say is the following. So we're going to have to move into, say, R9, the length of input. So R9 now also contains the length of the input, and then we are going to pass R9 into this. This way, R9 contains the value, not the memory address of the length of the input, okay? And so after this, we see that on the right-hand side, we need to initialize the I. And to initialize the I, we can use the memory, the register, say R8 for the counter. Okay, we can use this as a counter. Okay, and then we enter into a loop, which is the while loop. And in the while loop, essentially what we're doing here is we are entering into a loop. This way. Yep, we're entering into a loop. And in the while loop, we are comparing I to the length of the input. And so in order to do that, it's quite simple in Nasm. What happens is we have a few operations that we can do. So we have the CMP, which means compare, which is akin to using if condition, okay? So we're saying compare R8 to the length of input, okay? And then we jump if it's greater than or equal to like the end, which is done. And in the done, we're going to have to print it out. That means if the I is greater than or equal to the length of the input, we are skipping this loop, we are breaking out of this loop, and then we are printing it back to the screen. So writing back to the screen, we have done. And in the done, essentially we're doing move array axis right, and then move RDI standard out, and then move RSI, we are writing back the buffer, and then RDX will now contain the length, and then we're doing a syscall, and then of course we're going to exit our program, where with the exit we have the exit request, which is 60, we have RDI, which is 0, and then we do the syscall. The exit request over here is already defined in the constants. Okay, so over here what we're looking at here is, instead of writing say 1 and then the prompt, as we've already seen, we just defining a constant, so it looks much more, pretty, and looks like kind of like the C version, where we have the syswrite, the file name, sorry, the file descriptor, and then the prompt and the prompt length. So it's the same thing, the write, the file descriptor, the prompt, and the prompt length. So it's really nothing new. Okay, and so In the case where it's still less than, we have to look at the following. So if the value at this buff is greater than or equal to A, okay, then, and we also check that it's lesser than or equal to Z, then we subtract 32. What happens here is we also have to do another comparison. So what we're doing here is compare the byte buff plus R8, and then we say 97. Why 97? Because 97 is the ASCII character for small a. And then if it is, then we're going to jump to upper, where upper is the directive over here. We'll write it soon enough. And then in this case, and the other case, we're going to look at this, another else if, which is we're going to compare the byte buff plus R8, and then we're comparing it with 65, which is capital A, and 65 is the ASCII character for capital A. And then if it is greater than or equal to, then we convert the value to lower. Okay, then otherwise, if it doesn't fall into any of these two categories, we have to increase. Okay, so over here I'm going to call another directive to increase. Okay, so now let's work on the to upper. So in the case where it checks whether it's greater than 97, essentially what I'm trying to say over here is, over here we've already defined R8 to be 0, yeah, and so it's going to check, say, the buff with I equals 0, and then if it is, then it's going to jump into upper, and in the upper we can say we're also going to have to check for this particular line, which is the same thing, R8, and then we're checking it against 122, which is the ASCII character for small z. Okay, and then if we jump to increase if it's greater than, otherwise we subtract the byte and the buff plus R8, and then we subtract 32 from that, and then we jump to increase. Why 32 specifically? So over here, let's take a look at the ASCII table. We see that small a is 97, and then capital A is 65. Okay, so in the case where it's small a, we need to convert it to capital A. We subtract 32 with 97 minus 65, which is 32. In the case where it is greater, it's small, capital A, and we want to convert it into smaller a, we add 32. The same thing for the B, the same differences, and 32, 32. Okay, so that's why I'm using the value 32. Okay, and so yeah, we look at to increase, then we subtracted 32, we jump to increase. Okay, we can also write the to lower, where we have compare the byte buff plus R8, then we compare it to 90, and 90 essentially is that of the capital Z, as we've already seen. Then we jump if it's greater than or equal to increase, otherwise we add the byte to R8, and then we add 32 to that, and then we jump to increase. Why jump to increase? So now we have to write the directive to increase. Okay, so to increase, all we are going to do over here is we're going to increase I plus plus, which is essentially increasing I by 1. And we have a very simple operand, which is inc. And then we're going to increase the I value, which is stored in I8. Then we jump back to the loop. Okay, so we check, then we jump back to the loop, and if the condition is, well, false, then we break out. Okay, so it's the same thing. So essentially this whole section is the while loop, and then we do the checking, the if conditions, and then we do the conversions from the to upper to the lower. Then we exit when the condition no longer holds. Okay, so that's essentially the code. And once more, I would like to say that JMP essentially means jump, and JL means jump if less than, and JLE is jump if lesser than or equal to, JG is jump if it's greater than, and JGE is jump if it's greater than or equal to. So it's nothing really difficult, I suppose. And so let's save this, and let's try to compile this. This is inverse case and no errors. So we write, and then it says enter. Let's do more video, and then we see that we've been able to successfully do the the inverting of the cases. Okay,